Hey guys, welcome to another video that I will be teaching stats. And today's lesson is about error and power. And we will never know the truth when we perform significance tests, and we draw the most logical conclusion based on our sample evidence, aware of the possibility that our conclusion may be incorrect. We must explore the types of errors that can be made when performing hypothesis tests. So basically, these paragraph is just saying that whenever we're implement an experiment in stats class, we are not 100% sure. In fact, we will never be 100% sure about our results. It will always be off from the truth a little bit. It's a lot of times it's not due to our personal errors, it's not due to human errors, it's just some like inevitable errors or like random errors that we cannot eliminate. So like in order to be more precise, we want to calculate how like what amount of errors can we avoid and what types of errors can we avoid, and if some errors are unavoidable, then how close are we from the truth. So let's dig into it. So first of all, I created this table right here. In here it's labeled as truth, and in here is the decision. And we're going to introduce two types of errors, basically. One is the type 1 error, and the other is type 2 error. And the type 1 error occurs when we reject the null hypothesis when it is actually true. So, which means that when H0 is true, but we somehow reject H0, and then in that situation we made a type 1 error. One real-life example would be send a innocent man to jail. Definitely, it's not a good consequence, but it's just somehow like unavoidable errors that will occur when we implement those experiments. The other type of situation will be the null hypothesis is actually false. I'm sorry, but we somehow reject it. So then it's good, right? We made a correct decision. So that's called power. Power is actually the ability, or you can say like power is actually when like null hypothesis is false, and then the alternative hypothesis is true, and you correctly reject the null hypothesis, then you implement your power into this situation. And this is a very good decision, and we want more power when we're making these stats deals. So a real-life situation will be send the guilty man to jail, and the other situation will be the null hypothesis is true, and we fail to reject null hypothesis. And this is also a correct decision because we know that our original decision, or like the original decision of that situation is correct, and we fail to reject our alternative. We reject our alternative hypothesis, and we fail to reject the null hypothesis, which means that we make the correct decision. We haven't changed anything, and that's the right way. Real life example will be send the innocent man set free, and this is good. Last but not least is going to be H0 is false, but we fail to reject H0, and this is called a type 2 error. This will be send the guilty man, let the guilty man set free, which is not a good thing, right? Because in reality, we know, we don't know actually. If we are the experimenter, we don't know, but in reality, this man is guilty, but we cannot, but we cannot we cannot determine the crime on him, so we just let him free, and it's not a good decision. So those are the mainly 4 situations you'll be seeing in real life in your statistic classes. And we're moving on. And here are some definitions. The power, just as I said before, is the probability of correctly identifying a false null hypothesis, which means it's kind of like mouthy, but when we say that we have more power, which means we have more chance, or we have higher chance or more ability to reject the false null hypothesis, which means that we have more power. And the type 1 error, we can also label it as alpha. Looks like an A, but it's actually it's like a fish. And type 2 error, the probability of type 2 error plus the power is equal to 1. So always remember these two add up to 1, not type 1 and type 2 error add up to 1. This is wrong. I know they seem like very complement to each other. A lot of students will mix up those together, but this concept should be clarified. Okay, let's moving on. So let's actually dealing with an example, because practice makes perfect, right? So then this is a potato chips problem, and I label the key terms in here. The key information has been provided in here, which is the mu is equal to 2.0 mg per chip. Mu is the population mean, and the sample size is 50. Is the lower sodium chips, and the sample mean is 1.98 mg per chip. The standard deviation is 0.1 mg per chip. The alpha is 0.05, and we can also say this is the significant level. They are exchangeable meanings. So what's our population mean? Well, it's the average sodium content in lower sodium chips. And we are setting up the null hypothesis will be we know that the sodium in every chip will be 2 mg, which is given up right here. And the alternative hypothesis, which we want to testify, is going to be we want to know if it's less than 2 mg per chip. And this is what we're gonna setting up our test. So what's the name of our procedure? This is the z-test for 1 mean, and the alpha will be 0.05. This is the significant level. And we're checking our conditions right here. So first of all, is this a simple random sample test? It is, we assumed. And the second is that is the sample size less than 10% of the population? Well, there is more than 50 chips because we only use it should be like a 500 in here. I'm not sure somehow I wrote it in this way, but it should be 500 because we want to know if it's 10%, right? So we are using the sample size of 50, so this should be 500 chips, and more than 500 chips. I mean, definitely. So then standard deviation will be 0.1 divided by square root of 50. So then n is the sample size. The 50 is greater than 25. You can also say this is 30. It depends on your textbook and your professor's teaching way. But I'm stating here is 25, and which means that sample distribution is proximally normal because the sample size is large enough that even though the original population is skewed right or left or like just not normal, because the sample size is big enough, we have the confidence to state that the sample distribution is approximately normal. Okay, so then we draw our graph in here, and the z-score in here, we will use x minus mu divided by standard deviation, delta, and we get negative 1.41. And in here, this is the x bar, which is the sample mean, because we want to know that if the mu is less than 2, so we will shade it to the left region, right? If it's greater than, we will shade it to the right. And the p-value in here will be 0.0786. How do I get this number? Well, you just enter this on your calculator, normal CDF, and enter the standard deviation and the mean and the sample mean, and just make sure that is to the left region, like less than 1.98, and you will get this value. So we finally can draw our conclusion right here. So I will write it like this. Since p is equal to 0.0786, which is greater than alpha equal to 0.05, we fail to reject null hypotheses. We cannot say the lower sodium chips have an average sodium content less than 2 mg per chip. And like following up, I mean, this is a complete procedure right here. We have the state, we have the plan, we have the do, we have the conclude part. I mean, everything is complete. But in real AP exams, you know, like they want to be fancy and tricky, so then they will ask some follow-up question. So for this question, as an example, what if they ask what type of errors this experiment will possibly be make? So how should you answer this? We have to look back at our conclusion part. Because we say that we fail to reject null hypotheses because p is greater than alpha, which means that this must, not must, but we have a high chance to make a type 2 error, because we say the lower sodium chips do not have a lower sodium content when they actually do. This is the situation when we made a type 2 error. Remember, type 1 error is also rejecting null hypotheses when it is true, and type 2 error will be not rejecting null hypotheses when it is false. So because in this case we fail to reject null hypotheses, the only possibility we can make is the type 2 error. We cannot make type 1 error or make these two like both at the same time. So either one of these or either one of this and no both. And so then people stop, and so what are some consequences? Well, people stop buying the chips even though they do in fact have lower sodium, and that's the case. So moving on to here, this is the graph I'm showing, the probability of a type 2 error, and you do not have to calculate the probability, but you need to understand where it comes from graphically. So how can we reduce the probability of type 2 error? Well, before I actually talking about this question, let's first take a look at this graph. So in the graph that it's on the left side, the mean is mu, which is the mean that is true, and in here is the this is the true mu, and in here this normal curve has the mean that is the null hypothesis mean. So then, because we want to know that when is the time to make a type 2 error. Type 2 error is, type 1 error is alpha and type 2 error is beta. Type 2 error is not rejecting null hypothesis when it is false. So then, take a look at this blue region. You are not rejecting the null hypothesis, right? But even though it is false right here. So this is the situation where you will potentially make a type 2 error. And in here, this is the case that you will make a type 1 error because you are rejecting null hypothesis while it is actually true. So to talk about this more briefly, to assume that this is a line right here, this line is corresponding to our original, this is the sample mean, right? This is the sample mean. So then if we want to say that, okay, this is, our alternative hypothesis is that the mu should be less, the mu should be smaller. So then we will shade the left region of the sample size, the sample mean, sorry. So then this region becomes alpha, and as we increase this vertical line, for example, visually imagine that it's line up there, then we will increase the alpha level, which means we increase the significance level, and the power is also increased. Let me let me go back through it. So power is always corresponding with the type 2 error. So type 2 error plus power is equal to 1. So if and also alpha and beta, type 1 and type 2 error kind of have inverse relationship, even though they're not directly inverse relationship, but they kind of have that. So if you increase alpha, you decreased the beta, and because the beta got decreased, the power will increase. Okay, so if you increase the alpha right here, remember power is that we know that our alternative hypothesis is true and we correctly reject the null hypothesis. So if we increase the alpha, alpha is rejecting null hypothesis, right, when it is true. So because we have a larger region for us to reject the null hypothesis, we have a higher chance of gain more power to apply to the situation. You know what I'm saying? So to rephrase it a little bit, if we increase the alpha level, we have more area in this graph to reject the null hypothesis, which means we have a higher chance to gain more power to reject the null hypothesis. Well, we don't care about if null hypothesis in this case is true or false. We just cared about, do we have more chance to reject the null hypothesis? And because power, the precondition for a power to happen is that we have to reject the null hypothesis. And because in this case, as we increase alpha, we increase the possibility that we reject the null hypothesis, which means potentially we will have more power. Okay, so let's moving on to the second question. How can we reduce the probability of type 2 error? Well, first we can make alpha bigger, and as I said before, the probability of making a type 1 error is alpha, and probability of making a type 2 error is beta, and they are inversely related. And the second way is to make our sample size bigger, because as you increase the sample size, the standard error will decrease, so the data will be more precise. The experimental results will be more precise. So then, if there is a chance that the type 2 error will happen, well, in that case, it will be more likely to happen. And the third way is to make standard deviation smaller. Okay, so this is kind of similar to the previous step, which if you make the standard deviation smaller, the data are more tightened up and they are more clustered, and more data will align to the real, more data will align to the real hypothesis. So then from step 2 and 3, we know that standard deviation of the sample mean will be equal to the standard deviation divided by the square root of sample size, which the standard deviation of the sample size will get smaller. Okay, so just to reinforce right here, power is the probability of rejecting null hypothesis when it is fake, when it is false. and this can also be interpreted as 1 minus beta. Okay, so that's all for today's lesson. Thank you so much for listening, and stay tuned. More videos will coming up soon, and I hope you learned something from this. Thank you.